Okay, so good morning, everyone.
Good morning, ma'am.
Good morning, ma'am.
Morning, ma'am.
Cool. So, yeah. So I hope you guys have been doing the assignment, and yeah, I hope there are no issues with the assignment and things are clear. So please contact me if something is still unclear. So the date for submission is the coming Tuesday. Okay. All right. So let's get started. So I think the recording is on and screen is shared. Okay. Okay. So yeah. So in the last class we were looking at the steepest descent, and we looked at quadratic functions. And we saw a way to set the alphas. So the updates were of this form, and dk in particular was something like this, right? So in steepest descent we had dk was negative of grad fk. Okay, and we saw a particular example of quadratic functions, and we saw how to set the best way to set alpha in that case. We got a closed form expression there. Okay, so today, and yeah, we also discussed some things about the rates of convergence. And in particular, we saw something about the steepest descent algorithm. So let me just bring back that result once. Sorry. Yeah. So the result, so I didn't go into the proofs of the rates of convergence because, I think like at this stage, since most of you are doing a first course in optimization, so I think it's important to get a sense of a broad set of techniques. Okay, so the convergence results go in depth into one of the technique and try to do an analysis. So this is useful, of course, later if you want to do some kind of research in the field of optimization. And of course, the derivation is useful in that sense. But of course, the main result of what the convergence result is, that is useful if you want to apply this in various places. And steepest descent is one of the very popular approaches. Okay, so you will see it getting used a lot if you're doing the machine learning course. Okay, so so this is the sort of result we had for convergence, where it depends on the eigenvalues. So maybe at a later point we can just come back to this algorithm. If you want to go into more depth here, if there's time. Okay, so now what?
Ma'am,
Yes,
ma'am. Here
yes,
in the
yes.
third example, in that particular only, in the third example, you said that a square by a to the power 2k is less than 1. I think that is not less than 1 because a lies between 0 and 1. So that would not be a quadratic convergence here.
Okay, so you're talking of this example. Okay, so let's just
Yes,
see. I
ma'am.
mean, I might have done some mistake also when I wrote it. So maybe let's just go through this once. So this was one. So let me just write the steps again. Okay. So what was it? We had one, a power 2 power k, right? So k plus 1 minus x star was a power 2 power k plus 1. And this was a power 2 power k, right? So this was into 2 you had here, right? Okay, and this was a square, so that's what this came. And so this is same as you could write this as into 2 here, right? So this is actually 1, right? Yeah, I think in the last class I probably did a mistake when I simplified this. So, so you see xk plus 1 minus x star, you will have a power, this is right, na? 8 power 2 power k into 2 here,
Yes, ma'am.
right? And in the denominator, you have again the same thing, a power 2 power k square, but it becomes of this form into 2 again, right? So then it becomes 1, right? So I don't know what I think we did some mistake in the last time. Rajneesh, this is okay?
Yes, ma'am. Okay.
Okay, so let's maybe just also see some higher power. So suppose you say this is some p, xk plus 1 minus x star per p. What happens? So this is in way for sure it's quadratic. But if you try to substitute some p here, what happens? I think that's when what you said will apply. So this will be some p here, right? And if p is greater than 2, then this will be smaller, right? Because a is less than 1, right? So any power of p greater than 2, if you put, this is not going to converge. And this will be 1 only if p is 2. Right? Rajneesh, this is okay?
Yes, ma'am.
Okay, yeah. Yeah, thanks Rajneesh for bringing this up. So I'm sure many of you would have had this kind of a confusion. I kind of quickly rushed through this in the hope of doing the next result. But yeah, this is important. So yeah, so the general idea to see things like rates of convergence, to prove a rate of convergence is to take this quantity, right? Xk limit k tends to infinity, xk plus 1 minus x star by in the denominator you take xk minus x star power some p. Okay, and the idea is to see what is the largest value of p for which this limit is finite. Okay, so that would be the rate of convergence, and the factor would be this value of limit that you get here. Okay, so that's the idea of how you prove convergence results. Okay, so now coming to this is what we said about the gradient descent method. We just kind of stopped it with this convergence result here. Okay, and we also had this global convergence if and only if this is true. Okay, so today what I want to do is I want to talk of another method, the Newton's method. We had briefly talked about this earlier when we looked at one-dimensional optimization. So now I just want to bring your attention to the case of multivariate optimization when you have multiple variables. So it's an extension. I mean, the idea is the same as what you had, but let's just go over it once. So you remember in steepest descent, we had this kind of a direction. The negative gradient was the was the direction you took. And we also saw that, if you multiply this, like some b times grad fk. Okay, so if you have a direction like this, when b is, positive definite, okay, then this is also going to be a descent direction, actually positive semi-definite. Right? Okay, so if this is the case, then this is also going to be a descent direction. Okay, so an example of that setting is the case like this, when dk is minus, this is a Hessian evaluated at xk, and the inverse of the Hessian. Okay, so if this Hessian is positive semi-definite, then you have that this is going to be a descent direction. Okay, now in particular, how did we come to this kind of a form? So this is from the Taylor series approximation. So this is kind of what we did for one-dimensional case, and the same idea extends for higher dimensions, where you take the Taylor approximation around xk, the quadratic approximation. So that's given by this form. So f of xk plus gradient times x minus xk plus this quadratic term. Okay, so now this is a good approximation. Okay, so you consider this as a tight approximation, and then you find an x such that the gradient is 0. Okay, so yeah, so suppose you take that this is positive definite. So I think this is positive definite itself, not positive semi-definite. Okay, so positive, you take that, suppose the Hessian is a positive definite matrix. So then what you need to do is you find the x such that this right-hand side, it also has a gradient of 0. Okay, so now if you take the gradient of this term, this approximation, what you get is grad fx, and that is 0. You want that to be 0. And if you take the right-hand side, the gradient of that, so this is a constant. So this is a constant, and so you're taking the gradient with respect to x. So if you take this term, there's only this term, the gradient of fxk, gradient of f evaluated at xk. And when you come to this term, you will get the Hessian times x minus xk. Okay, if you take the differential with respect to x. And the idea is to set this whole thing to 0. And so you try to solve for x. You need this x, which makes this whole right-hand side 0. So what you get is x minus xk is just, it's you just move the gradient to the other side and, multiply with this gradient, the Hessian inverse on both sides. So this is what you will get. Okay, so that kind of gives you the next step. Okay, so xk plus 1 is xk minus the Hessian inverse times the gradient. Okay, so that's the derivation for and the motivation for why you use the Hessian here. Okay, instead you can use any positive definite matrix. So yeah, your rates of convergence, if you use any random positive definite matrix also it will work. But you ideally want to have that matrix to have something to do with the function. Okay, that's when you have some improvement, you get benefits out of it. So that's where this makes sense. Okay, and so here what we have seen is alpha is 1. Okay, if you just use this update, we are not having any step size factor here, but in principle you could also try to use different kind of step sizes here. You could do things like this exact line search, or any of the other methods like constant step size and stuff. So that's also possible. So these things are kind of general, like for any descent direction you could try different step sizes and so on. Okay, so is this fine? Any questions so far?
Ma'am, when we are taking this approximation, what is exactly happening? I'm not able to visualize.
Okay, so maybe let me just illustrate it maybe. Okay, so let's take, you have this function over here, so something like this. Okay, this is a function that you're trying to minimize. And at this point, maybe you're somewhere here. Okay, so this is xk. Okay, and you have some, so yeah, at this point, you're trying to see where you want to go next. Okay, now if you look at you remember from the Taylor series approximation, and you possibly, also you must have tried it out now in the assignment. So if you think of a quadratic approximation to this function at this point, okay, what it will look like something like this, right? Something of this form. Okay, so this will be an approximation. So this is f of x, and this is this quadratic approximation to f. Okay, so quadratic approximation at x, at xk. So now what you're trying to do here is, so this function is exactly this right hand side, this one. Okay, so what you're trying to do is you're trying to go to the minimum of this. Okay, so somewhere here you reach. So that is your next, your estimate of the minimum when you are at xk. Okay, so somewhere here. So this is going to be your next xk plus 1. Okay, so now after this you come here, and again you construct the next approximation at this point. Okay, so my drawings are a little bad, especially I'm doing it on a tablet, so it's extremely messy, but the idea is this: you construct the quadratic approximation and try to find the minimizer of that approximation, and that's your next point. Okay, and you keep doing this. So now for this function, if you take the minimum, it will be somewhere here, right? And so you assume that, okay, that is going to be that's your estimate, that's your best you do from at xk plus 1. If you're asked to say what's the minimum, okay, that's what you do. Like, it's a local approximation and you're trying to minimize that. So like that you keep proceeding, and again, you at every stage you construct a quadratic approximation. And the thing is, this is a minimizer. So the point constructed in this way, so remember like what we did was just taking this right hand side and we took its gradient and we set it to 0. Okay, so so now you remember from our necessary and sufficient conditions, it's not guaranteed, right? Okay, this could also be a maximum if the gradient is 0. But that's not the case because of this condition. So because this is positive definite, okay, so that ensures that, you know, by setting the gradient to 0, you are indeed touching a local minimum of the quadratic approximation of this right hand side. Okay, so that's why it works. So at some point, if you have, you know, the second order approximation, if it's not having this form, in the sense that if the, you know, if this condition doesn't hold, then you may not be guaranteed to, you know, move. It may not even converge. Okay, because you might end up maximizing this function. So that can happen maybe for some example like this. So let's start with a different one. So something like, say, some function like this, okay? And maybe you have something here, you're at xk, this is your xk. And maybe you want to come here, right? And the quadratic approximation here would be something of this form. Okay, so now by maximizing this, you're going into some point here. Okay, so maybe this is still okay. Okay, this example is bad, but the idea is, you know, if you have, you know, the local maximizer, so it could be that, you know, if you're very close, maybe somewhere here at this point, right? Okay, so yeah, this is a function, suppose I'm considering, and suppose the quadratic approximation is something like this. Okay, so you wanted to go here, so this was the x star. Okay, you were on this side and you wanted to come here, but the quadratic approximation says that this is the next point. So this is the max. Okay, instead of the min, that's what you're ending up finding is the max when you set the gradient to 0 and you're moving away. So then it will not do well. Okay, so yeah, so that's kind of the idea why you need this to be positive definite. Okay, so that was this clear? Did it make sense?
Yes, ma'am. It was clear. And ma'am, one more question. There was a
Yes.
transpose in one of the steps. I couldn't catch it.
Which one?
So in the so when we took grad of f of x, f of x, then the equation on the right hand side was grad fx transpose x minus xk. So how did that change to grad fxk when we took the
Oh,
derivative?
okay. So this one you should, okay, try to view this as, you know, what this means like this. If you take, this is a linear function in the x. So let me just spend some time here. So this term is just, so if this is x is in n dimensions, so you have I, it's a summation, so grad f of x. So this is the ith term in this vector times xi minus xk. So xk ith term of x. Okay, so let me just move this. Okay, so this is just the summation grad fk, and this is the ith term of this gradient times x minus x. So this is the ith term of xi minus ith term of xk, right? And this is a summation. So this, when you write grad of x transpose x minus xk, what we mean is this summation. Okay, so now if you take the gradient with respect to xi, okay, just take the ith component with respect to the ith component, what are you going to get? You're going to get grad fk, right? The ith term of grad fki. So the first term, if you take it with respect to x1, so when I say x1, I mean this. Okay, so with respect to x1, if you take, what you're going to get is grad fk, the first term. Okay, the first component of the gradient vector, then you will get the second component.
Okay,
if you
ma'am,
take,
got it. Yes, ma'am.
okay, yeah, so that's how you get this. And similarly, even this one, when you evaluate it, you're going to get it in this form. Okay, so again, so if I'm sure many of you might have this question, so the way to check this is also elaborate, expand this in a similar way. So this is linear function, and this is going to be a quadratic function in x. So just expand it out and you will see that when you take the gradient, you're going to get this. Okay. Yeah, so thanks Siddharth for asking that. So any other questions till now? Is it all clear? Let me
Yes, ma'am.
ask somebody. Rohit is clear. What about Kaushal? Okay, Kaushal, you're there? Okay, you can type in the chat box if your mic has issues or anything. Okay, I don't hear from the rest. Devyani, it's okay?
Yes, ma'am.
Okay. What about Kshir Sagar? Siddharth is clear?
Yes, ma'am, it's clear.
Okay. Okay. So, yeah. Okay. So, yeah, I guess it's clear. Lakshmi is also saying it's clear. Fine. All right. So this is about the Newton's method. So, remember like last time I showed you, I just gave you a demo of the steepest descent. So similar thing, you could try this Newton's method also for those functions. And it's an alternate method. Okay. So another thing, so these are different methods. So why do we have so many methods? Because, each method performs differently, with different functions. Okay, so we saw a convergence result for steepest descent. Now for Newton's method also there is a convergence result. But what it says is that suppose, for general functions, if you have that this is invertible, the Hessian is invertible, because that's the only time you can apply this, right? Otherwise it's, it doesn't even make sense. So Hessian at which point? So at the local minimum, at x star, at the point of convergence, if it's invertible, then the result is that, there's a small region around the x star, such that if you had started from there, then you will get this quadratic convergence to x star. Okay, so it is a faster method because it has a quadratic convergence to x star. But one caveat here is that it's very important that you start from a point which is very close to x star. Okay, so of course this is not something which you can check, right? Like, you can't set an initial point close to x star if you already don't know x star. So if you know x star, then okay, you already know x star. So what's the point in doing this, right? So that issue is there, but this is an, it's a kind of result that you have in hindsight. So, yeah, this is a good method provided you initially started off close to the optimum. Okay. Yeah, so and it's good in the sense it's also quadratic. Okay, so you will also see this. I mean, I think the best way to understand these kind of convergence result is to implement it for different functions and see how many iterations you take and how long it takes. I mean, even it's quadratic convergence in the sense like the number of steps will be low, but what is the cost of each step? So that it has a this inverse computation, right? So you should try to see for larger dimensions what happens, how expensive is each step, and those kind of things. So that's the best way to understand this kind of a result. Okay, so anyway, you will see this in some assignments, the coming assignments. Now, I also want to draw your attention to another line search method. So line search is, these methods where you try to fix this alpha, the step size, those are referred to as line search. And why is it line search? Because, you're trying to find the best value of alpha, which is along a line, right? It's a one-dimensional optimization, and you want to, try to find this best value. So that's why they traditionally refer to it as line search. So we saw one thing which is called exact line search, in the sense that you found an alpha which exactly minimizes this function, right? So we did that for the case of steepest descent. So the flow of steps is first you have a descent direction and then you find this alpha. Okay, so we did that for steepest descent. We found the exact line search. But many times, this is not practical to exactly, minimize this f of xk plus alpha decay. Okay, because that again is another minimization problem. So in practice, what people do is they use different kind of heuristics. Okay, and one such heuristic is what is called this backtracking line search. Okay, so this is quite popularly used. So the idea is this. Okay, so you have this function. The one in blue is the function that you want to minimize. Okay, and so it's actually f, but you're writing it as a function of alpha. Okay, because you are currently at xk and you have a direction. So what you need to find is this alpha, right? So what's a reasonable alpha? So you write this as g of alpha, and this blue is actually just g of alpha, or it's just f of xk plus alpha dk. Okay. Now, yeah, you can construct a first order approximation for g of alpha. So the one in red here, so this is the point xk. So this is the point where alpha is 0. Okay, so I'm on the x-axis, I'm plotting the alphas. I'm considering the alpha. So at alpha is 0, so what we have here is just f of xk. So that is this value. Now you can construct a local approximation. So this is a linear approximation that I've considered here, the one in red. Somebody had a question? Shubham? Okay, Shubham, did you have a question?
No, ma'am. Sorry.
Okay. Okay, no worries. You raised your hand, so I was not sure. Anyway, so
By mistake, I
okay,
tapped.
no worries, no worries. All right, so yeah, so g of alpha was this function, and at the point alpha is 0, you can construct a first order approximation. So that's what we did with Taylor series, and that was something like this, right? So so this is what I'm referring to as a first order approximation. So that is just g of 0, because you're taking it at the point 0, plus alpha times the derivative at 0, right? So this is just from Taylor series. Okay. Okay. So now this g dash 0, right? So this is the differential of g at the point 0. So this can be computed using chain rule, right? So g is this function. And so if you take the derivative, what are you going to get? You just have gradient, right? Gradient of f evaluated at the point xk plus alpha. So let me just write it here. So g prime of alpha, can somebody tell me what it is? We use chain rule, right? So
F dash of xk plus alpha dk.
so f dash, so this is a gradient in multi-dimension, so I will write it as gradient. So what you're taking the gradient of is this inner, with respect to this inner thing, so that's a vector. So that's where this is a gradient. And this is evaluated at the point xk plus alpha dk, right? Then
Times dk.
times dk, right? So this is transpose dk. So dk is a vector, and this is also a vector. So you have this operation. Okay, so this is g prime. And now you're taking g prime at 0. So what you're going to get is just this. So substitute alpha as 0 here, and you're going to get a gradient of fxk transpose dk. Okay, so now one thing here is this quantity, this gradient fxk transpose dk, this is going to be less than 0. Right? Why is that? Any thoughts? Why is this going to be less than 0?
It's a descent direction.
Yes, exactly. So from what we did, like I think about 2-3 classes back, we said that dk is a descent direction if you have this condition, right? So yeah, since this is a descent direction, you have that this is less than 0. So that's why, I mean, so this has a slope. So this is the slope of this line, right? So this is a linear function in the alpha, and the intercept is this g of 0. So that's what is this one. And the thing. And now another thing you can consider, another line over here you can consider is the same thing, g of 0. But here, instead of taking g prime 0, you multiply it with some c. So c times g prime 0. Okay, so this is a new line. So this is g2 alpha, which I've shown in green. So this is g2 of alpha. Okay, so this is a new line with the same intercept, but the slope is c times g prime. Okay, so remember g prime was less than 0. So c is something which is between 0 and 1. So if you take c times g prime, that has a larger slope, right? Because this is negative. So something like maybe this value could be something like, say, minus 1. Now if you take c times that, maybe something like minus 0.5. Okay, so the slope is larger than this one. So that's why the line lies like this, above the original line. Okay, so this backtracking line search makes use of this G2 alpha as a reference point. So in the sense, you start off with some alpha here. Okay, so maybe something here. Okay, this is your initial alpha naught, and you evaluate the function value here. Okay, so this is here at this point. Now this is going to lie above this line, right? So the value evaluated of G2 alpha evaluated at alpha naught is this point. Okay, this value. So this is the function lies above this. So you say that, okay, this is not acceptable. You try to reduce it further. Okay, and so when you have that the function value exceeds the value of G2, you try to bring it down. You multiply it with a fraction, which is a fraction basically, value of rho between 0 and 1. So you try to reduce it further. Okay, now again you do this, and again you have this is still lying above. So maybe you reduce it further and so on, and finally till you reach a point somewhere here where you are below this line. Okay, so the idea is you always want to be within this. So you want the you don't want a step size greater than this. So you want to be in this interval. So your next point has some function value like from one of these. Okay, so that's the idea behind this, because you don't want a very large step size because you might just cross over the minimum point. Okay, so this is the backtracking line search. So if you start from an alpha like reasonably large, you'll finally come down. Okay, so usually you can start with alpha as 1, because then you're guaranteed that at least you have a descent direction, right? And so alpha is 1 is alpha equal to 1. Alpha not equal to 1 is a usual choice that people make. Okay, so like this, there are several other strategies. So another strategy is something like you consider one more reference point here. Okay, and now you don't want the decrease to be too small also. So you consider something in this range. Okay, so now in this backtracking line search, we allowed anything from between alpha 0 to some point here which achieves a decrease. Now you might also want some minimum value, say alpha is like 0.2 or something of that sort. Okay, so you want some guaranteed amount of decrease. So then you can have another reference line here and take any alpha in this range. So that is another thing. It's called Wolf condition. So there are several such heuristics people use. So I just wanted to introduce you to this one because this gets used a lot in machine learning. Okay, so a good reference for this line search methods is the book by Nosidol. Okay, so yeah, if you're interested in other strategies, that's one you could always refer to. Okay, so any questions on this?
No.
Okay, that's clear to Rohit. What about others? Tushar, is it clear? So that's clear. Good. You can just type here if it's clear. Tushar, it's clear. Okay. Bhavna says it's clear. Okay. Okay. Yuvraj also is clear. Okay. So now, so these are two descent methods we saw. Now there are many others in fact. There's a coordinate descent method, then there's a conjugate gradient, and there are these quasi-Newton methods. There are so many methods out there. So I wanted to cover something like conjugate gradient and coordinate descent if possible, but I also want to cover some of the other aspects in optimization. So maybe again, those are some topics we'll try to come back to at a later point. Okay, but I hopefully this should give you an idea of the kind of things that go on, and if need be in future, I mean, I hope you will also be able to pick up the other methods now that you have a foundation for this. Okay, so with this, I will move on to another topic. So we have always been talking about, like things like convexity. I've mentioned it to you in, at different points in the course, but now let's just try to understand a little further about what convexity means. Okay, so yeah. So we'll begin with this. So yeah, this is an an allied topic, I would say. So convex optimization itself is another class of optimization, and it's a very well studied topic, and it comes up in various applications. Okay, it's not only in computer science, but I think in other engineering fields also, like electrical and even industrial engineering and so on. Okay, so this is an important class mainly because for some groups, for some classes of convex optimization problems, there are efficient solvers. Okay, so and that is a big class of functions for which there is there have been efficient solvers. So that's why there's a lot of emphasis on this. So we will just touch upon some aspects of convexity in this course. So because it's not a fully, it's not fully focused on convex optimization, this one. So just some idea on this. So let's begin with convex sets. Okay, a set omega. I mean, you say it is convex if if you take any 2 points, then you have this relation. So this lambda x plus 1 minus lambda y, this combination of these 2 points will also lie in omega. Okay, and for all lambdas in 0, 1. So what does this mean? Let's just try to understand this condition. So this lambda x plus 1 minus lambda y, it's nothing but it's just the line joining x and y. Okay, so for instance, you could, so another way to view this is, this lambda x plus 1 minus lambda y. So you can take it as y plus lambda times x minus y. Okay, so I'm just rewriting this, right? So what this means is you start with y and you have some lambda and you scale this vector x minus y by this lambda. Okay, and you add that to y, what you get is the new point. Okay, and the idea is that also belongs to omega. So if you set lambda as 0, what you're going to get is just the point y. Okay, so it's just 0 x plus 1 y. Now if you set lambda is 1, okay, so what you're going to get is the point x. So that's like the two limits of the values of lambda, the two extremes of lambda. And for everything in between, you're going to get something on this line. So what convex sets are is that if you take any 2 points, the line joining them also belongs to the set. Okay, so this is for 2 points, and this combination, right, this lambda x plus 1 minus lambda y, this is called a convex combination of these points. So you know about linear combinations, right? So in linear combinations, you just had something like, remember linear combination was just something like alpha, sorry, just writing it sigma. So alpha x plus beta y, something like this. And there was no restriction of alpha and beta, right? So convex combination is a special case where you have these alphas and betas are positive and they sum to 1, okay, because you want it to be on the line. Okay, so now an analogous thing you can do for multiple points. So this, whatever I told you here was for 2 points. Now if you have multiple points x1 to xn, what does a convex combination mean here? Okay, so the idea is same. So what you just take is you look at all points such that you can write it as summation lambda I xi. Okay, such that all the lambda i's are greater than 0 and they sum to 1. Okay, so it's just a generalization of whatever I showed you for 2 points. So this is what it means for if you have multiple points, this is what it means. Okay, so yeah, so every convex combination of points will belong to the set omega. Okay, if it is convex. Okay, so let's just see an example here. So if the set looks like this, so I'm just showing you with respect to the geometry. So if the set looks like this, okay, and you have the set is like all the points within this. Okay, it's an ellipse or circle or I don't know, something of that form. Okay, all the points inside are also members. So this is a convex set because any 2 points you take, okay, and you take a line joining them. Yeah, this is my drawing skills. Okay, so supposed to be a line, okay? So this, any 2 points on this line also belongs to the set. Okay, you take any 2 points here. Now this also belongs, any line, and any point on this line also belongs to the set. So that's true for every point, okay? Every combination of points you take, it's the case. Now similarly, this is a polygon, okay? And here also, if I take all the region inside the polygon, that's a convex set, okay? Now what about this? Can somebody tell me, like this is now the polygon and I'm taking only the points on the boundary of this polygon. So is this a convex set?
Yeah, ma'am.
It's not a convex set, right? Because you take some 2 points here. Anything that you draw in between these two, that doesn't lie in the set. So it's not a convex set. So what about this one? So here, suppose I'm going to take the whole region inside. So if I don't consider the region inside, it's not convex because of the same reason. What about this one? If I take
Still
everything
not
inside,
convex, ma'am.
still not convex. Why?
The top part, right side top part to right side bottom part, if you connect.
There's something like this, right? If you draw like this line doesn't belong to. Okay. So now, many times you are given things like these inequalities, okay? Like something of this form. So x1, x2 in R2, where x1 is greater than or equal to 0, x2 is, positive, and x1 plus x2 less than or equal to 1. Okay, so that is this region that I've shown here, because x1 greater than 0 is this region. This is x2 greater than 0, this region, and x1 greater than 0 is this region. Okay, now x1 plus x2 less than or equal to 1 is the region to this side of this line. Okay, so something which simultaneously satisfies all this is this shaded part here, and this is also convex. Okay, so these are some examples here. Now I'm taking the same example here, but instead of considering I have some more restrictions that x1 and x2 are maybe not 0, 1, it's just integers. So okay, let's say x1, x2 are integers. Okay, so is this a convex set? So the region I've shown is like this, the ones in red. Is this a convex set? I didn't hear you.
No, ma'am.
Just the red ones, they are not convex, ma'am.
It's not convex, right? So so that's a subtle difference between these two, right? So this here, the whole region was continuous and you had a convex region. Now here it's the same region in some sense, but you're only looking at some points here, only the integer points here, and this is not a convex set. Okay, so now we have something called a convex hull. Okay, and this is just the smallest convex set which contains omega. Okay, so for the case of this example where you had these integer points, the convex hull would be all of, if you, basically this one. Okay, so the convex hull of this set is basically this set without the integer constraints. Okay, so that's, basically the smallest convex set which contains omega. Okay, so what about for this one? No, this is the set I showed you earlier. So what is the convex hull of this thing? Visually, if you see, it would contain everything here, right? It would be the shaded part would be there. and also you need to enclose these within. Okay, so that would be the smallest convex set containing omega. Okay, so we'll come to convex hulls, in a little time. Now, another thing to remember is if omega is already a convex set, then its convex hull, of course, is omega, because the smallest convex set containing it is itself. Okay, so this will come a little later. So maybe I'll just move on to the next topic, which is convex functions. Okay, so what we saw was convex set, and now we'll see what is a convex function. So function is convex if, of course, the domain of this function is a convex set. And any 2 points you take here, you evaluate this one, right? So lambda x plus 1 minus lambda y. So this belongs to the domain because the domain is a convex set. So that's why you need this. And additionally, what you have is this function, when you evaluate it at some point between the two, it lies below this this is also a convex combination. So it lies below this, okay, the right hand side. So let's just see what this means graphically. So lambda x, so there are 2 points here, x and y. So if you take lambda x plus 1 minus lambda y, you have this point z. Okay, so something in between. Okay, so now this is the function. Okay, if I evaluate f at z, what I have is this point. Okay, this is the function value. Okay, now if I take on the other hand, so this is f of z is what we have on the left hand side here. Now on the right hand side, what I have is this convex combination of f of x and f of y. So f of x is this value, f of y is this value. Now take the line joining these two. Okay, so the convex combination, the same combination of those two is this point here, okay, which lies above, above this function. So the what convexity is telling you is this f of z, the function value here lies below what you would have gone with the line joining the two. Okay, so that's the idea for convexity. Okay, so is this definition clear to you all?
Yes, ma'am.
Okay. For the others, it's okay. It's all good. Yes. Okay. Okay, good. Okay, Devansh also said it's good. Fine. Okay. So this is the idea in convexity. So it's somewhat like, it's usually represented by these kind of bowl functions. Okay. So where this relation kind of holds true. Okay, that's a quick way to see convexity. You take the function and you take the line joining any 2 points, it lies above the function. Okay, so now if you look at this function, this is not convex. Okay, because if you take a line joining these 2 points here, it lies below the function. Okay, so that's why this is not convex. Now again, this is also not convex because if you take some any 2 points you take. Okay, so there are 2 points. There exist 2 points such that if you take the line joining the two, it lies below the function. So that's why it's not convex. So in fact, this kind of a structure here, if it's true that any 2 points you take, the function will lie above the line. Okay, so you'll have the reverse of this inequality. Okay, such functions are called concave functions. Okay, and a function is concave if the negative of the function is convex. Okay, so you'll have like an inverted bowl shape. Okay, so intuitively. Okay, so that's about concavity. And the feature about these optimization problems, why these are important, is that if you define an optimization problem like this as a minimization of a convex function, and over a convex set. So the constraint set is convex and the function, objective function is also convex, and you're trying to minimize it. So then any local minimum also is a global minimum. Okay, so you recall that, when we started unconstrained optimization, we talked about, optimum at a local point and something which is globally optimum. Okay, and you can have local minima, but not global minima, right? But turns out for these kind of problems, this doesn't happen. Okay. So the proof idea is simple. So I'll just try to finish this proof and then we'll stop. So the idea is just it follows from the definitions. Okay, so suppose it's a proof by contradiction. So suppose X is a local minimum. So what it means is that you have a neighborhood around it, such that in this neighborhood, X star is the best. X star has the lowest value among every other point in this neighborhood. Okay, but globally it's not the minimum. So that means there is another point Z, okay, such that f of Z is the global min. So Z is a global. So let's say Z is a global min. Okay, so it means that f of Z is less than f of X for all X in the set. Okay. So now what you can do is, if you just take the line joining the two, okay, you take X star, that's a local minima, and you connect it with Z. So any line, any point on this would be something of this form, right? So Y is X star plus lambda times Z minus X. Okay, so that is a point which lies on this line. Now, what we have is f of y. So by convexity, what we have is, so this is what? This is just lambda z plus 1, sorry, this is also x star. So plus 1 minus lambda x star. Okay, so f of y is just going to be lambda times f of z plus 1 minus lambda times f of x star, right? Okay, so now you have that this is also true, right? Lambda, this is true by convexity. Now f of z, if you take, this is going to be less than or equal to f of x. Okay, so f of x star. Okay, f of z is going to be it's going to be less than or equal to f of x star. Okay, because f of z is less than or equal to f of x for all x in omega, and in particular this is true. And since x star, you assume that it's not a global min, so it must be that even it is strictly less than. Okay, because otherwise even x star would have also been a global min. So this is not the case. So this is going to be less than f of x star. So lambda times f of z is going to be less than lambda times f x star, plus again 1 minus lambda times f of x star. Okay. Now, so this is just nothing but f of x star. Okay, so what we have is f of y. We have found a point f of y, which is strictly less than f of x star. Okay, and y lies on the line joining x star and z. Okay, so this is true for any point y. Now, that is parameterized by lambda. Okay, so suppose you take, lambda is very small, like in particular so that the new point y lies within this ball. Okay, so then you have that for that point, f of y is less than f of x star, but that cannot be the case because x star was a local minimum. Okay, and within this epsilon, you have that f of x is any point you take, it's greater than f x star. Okay, but here you have a contradiction in terms of the point y. Okay, so that's why you can't have that for these kind of functions. Every local min is also a global min. Okay, so any questions here? So I'm kind of running out of time, but okay. All right, so yeah, I think I will stop with this because it's quite late. So if there are any questions, I will stay on. But otherwise, thanks for coming, and I'll see you tomorrow.
Thank you, ma'am.